What if everything we think we know about the universe is wrong, not just a little off, but fundamentally flawed, inverted in a way so profound that we've been living inside the very phenomenon we once thought was a cosmic monster? For generations, scientists viewed black holes as destructive endpoints of massive stars, places where gravity becomes so intense that not even light can escape, where matter is crushed to infinite density and time slows to a crawl before freezing entirely at the event horizon. But what if we've misunderstood their role in the grand architecture of the cosmos? What if instead of being isolated death traps scattered across the universe, black holes are actually the wombs of new universes, and we are living inside one right now, completely unaware of the unimaginable reality outside? This isn't just wild speculation from fringe theorists. Some of the world's most respected physicists are seriously considering the idea that our universe, the stars, galaxies, space, time, everything we experience exists within the event horizon of a colossal black hole that formed in a higher dimensional space. This idea, sometimes called the black hole cosmology hypothesis, flips our understanding of cosmology inside out and has profound implications for everything from the origin of the Big Bang to the possibility of an infinite multiverse. To wrap your mind around this, imagining a dying star in another universe collapsing under its own weight, reaching the critical threshold where escape velocity exceeds the speed of light, forming a black hole. From the outside, time appears to stop at the event horizon, but from the inside, something extraordinary might happen: a rapid inflation of space-time, just like what we observe in the first moments of our universe. The Big Bang might not have been the birth of all existence, but rather the bounce from another reality's collapse. Some models, like those proposed by physicist Nikodem Popowski, replace the singularity with a bridge to a new universe through torsion, a twisting of space-time that naturally arises when spin is included in general relativity. In these theories, black holes don't end in paradoxes, but act as portals or seeds for entirely new space-time bubbles, each with its own physical laws and evolutionary paths. That means black holes could be like cosmic seeds, each one blossoming into its own universe, and our universe could be the interior of one such seed, forever cut off from the parent cosmos beyond the event horizon. It also means that every black hole we observe in our own universe might contain entire new universes within them, inaccessible to us yet vast and real in their own right. The implications are staggering. Not only does this solve the singularity problem, it also explains why our universe appears so smooth and homogeneous on large scales. Just like matter falling into a black hole is stretched and smeared across the horizon, the initial conditions inside a black hole-born universe would be uniform, explaining the cosmic microwave background's surprising smoothness. It also offers an explanation for the arrow of time, which is one of the great unsolved mysteries of physics. Inside a black hole, entropy increases as space-time expands, just like what we see in our own universe. But there's more. If we really are living inside a black hole, then everything we observe, all of our physics, all of our measurements, all of our deepest theories, are taking place within a curved, finite region of space-time enclosed by a boundary we cannot cross, a boundary beyond which lies a larger, higher dimensional universe with potentially very different laws of physics. From our perspective, the universe is expanding at an accelerating rate, driven by something we call dark energy, a mysterious force that pushes galaxies apart and defies our understanding of gravity. But what if this acceleration is just a result of the way time behaves inside a black hole? From the outside, nothing escapes. From the inside, the experience could look exactly like an expanding universe. The horizon of the black hole from which we originated could correspond to the edge of our observable universe, the cosmic horizon beyond which we cannot see, not because of distance, but because of fundamental limits imposed by space-time geometry. There is even a striking resemblance between the equations governing black holes and those that describe our expanding universe. For example, the Friedmann equations that drive modern cosmology emerge from general relativity, the same framework used to describe black holes. And when certain boundary conditions are applied, these equations suggest that the universe behaves as if it were enclosed by a horizon with thermodynamic properties: entropy, temperature, and information contental concepts deeply tied to black hole physics. This leads directly to the holographic principle, an idea born from string theory and black hole thermodynamics, which posits that all the information inside a volume of space can be described by data encoded on its boundary, just like a hologram. That means our entire three-dimensional experience of reality could be a projection from a two-dimensional surface that might, in this case, be the event horizon of a black hole. This principle is not just philosophical. It has real mathematical backing and has been applied to black hole physics with incredible success, leading to the idea that space and time themselves might emerge from quantum information stored at the boundary of the universe. If that boundary is the event horizon of a black hole in a higher dimensional space, then our universe is not just inside a black hole, it is a black hole from a different point of view. Every law of physics that we obey, light speed, causality, the flow of time, may be local effects arising from a deeper reality that exists outside our visible universe. The consequences of accepting this theory are enormous. It implies that the Big Bang was not the beginning of everything, just the beginning of our local experience of time. It suggests that there is a larger reality out there, perhaps governed by laws we can only guess at, where black holes collapse to birth new universes in an endless chain of cosmic reproduction. It offers a solution to the question of what happens inside black holes, something we have never been able to probe directly, and it may even hint at a mechanism for the evolution of physical laws, where each universe carries slightly different constants, and only those conducive to complexity and life persist. Some scientists call this cosmological natural selection, and in that view, we live in a universe finely tuned for life, not because of chance, but because it descended from a lineage of black holes that produced viable universes. Of course, there is no direct evidence yet for this breathtaking vision. We cannot see beyond our cosmic horizon, and we cannot escape the bounds of our own space-time to verify what lies beyond. But science has often advanced not just by observation, but by daring to ask the most radical questions and pursuing their answers with mathematical rigor and intellectual honesty. The theory that we live inside a black hole is not just a bold idea, it is a logical consequence of certain extensions of general relativity, quantum theory, and thermodynamics. It has roots in our best theories and points toward a future where our understanding of reality may shift once again, not because we looked outward, but because we dared to look inward. The next time you look up at the stars, consider the possibility that what you're seeing is not the vast openness of a universe from the outside in, but the interior of a cosmic paradox, where everything we call real is just the inner life of a collapsed star in some unimaginable elsewhere, and that somewhere out there, beyond the edge of everything we know, is the truth we've been trying to understand all along. For most of human history, the universe was a mystery too vast to comprehend and too sacred to question. Ancient civilizations gazed at the night sky not as scientists, but as storytellers projecting gods, myths, and destinies onto the stars. The Babylonians mapped the heavens with extraordinary precision, not to uncover cosmic laws, but to divine the will of celestial deities. The Egyptians aligned pyramids with star systems, believing the soul would ascend through the sky to eternal life. The Greeks went a step further, not only naming the constellations but trying to explain the heavens through reason. Yet even Aristotle, the father of logic, believed in a geocentric cosmos where Earth sat unmoving at the center, surrounded by perfect, crystalline spheres carrying the stars and planets in divine motion. For nearly Cox, Nala years, the Ptolemaic system reigned supreme, a model of nested spheres that explained planetary motion with epicycles and deference, beautiful in its complexity, but ultimately flawed. Then came a seismic rupture in thought. Nicolaus Copernicus, in the 20th century, quietly proposed a heliocentric model where the Earth orbited the Sun. It was a dangerous idea in a world where cosmology and theology were indistinguishable, but it planted the seed of revolution. Galilei dared to look through a telescope and saw what no one else had: moons orbiting Jupiter, Venus going through phases like the Moon, mountains on our lunar surface. These weren't just observations. They were bullets fired at the heart of the old world. Galileo's discoveries gave weight to Copernicus' theory and shattered the illusion of Earth's cosmic privilege. Yet the Church condemned him for heresy, forcing him to recant. Still, the truth had escaped the cage. Then came Johannes Kepler, who deciphered the laws of planetary motion. discovering that orbits were elliptical, not circular, and Isaac Newton, who revealed the invisible force behind it all, gravity, a universal attraction binding the cosmos, governed by mathematical law. Newton's Principia Mathematica was more than a book, it was a turning point where the universe began to transform from a divine mystery into a mechanical system. For the next 2 centuries, science flourished. Telescopes grew stronger. Observatories dotted the globe. Humanity reached further into space with every discovery, yet still believed the universe to be static, infinite, and eternal until the 20th century cracked it wide open. In 1915, Albert Einstein unveiled general relativity, a radical new view of gravity not as a force, but as a warping of space-time itself by mass and energy. The universe was no longer a stage, but a dynamic actor in its own story. Einstein's equations predicted that the universe should be either expanding or contracting, yet Einstein himself couldn't accept either. Added a cosmological constant to force a static solution, only to later call it the greatest blunder of his life. Meanwhile, an American astronomer named Edwin Hubble peered through the Hooker telescope and discovered that galaxies were not just moving away from us, they were doing so at speeds proportional to their distance. The universe was expanding. This was 1969, and it changed everything. The night sky wasn't just a canopy of stars, it was a snapshot of a universe in motion, born from a single explosive beginning. This led to the birth of the Big Bang Theory, first proposed by Georges Lemaitre, a Belgian priest and physicist, who envisioned the universe expanding from a primeval atom. It wasn't just philosophy anymore, this was a scientific theory with predictions. And in 1965, 2 radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered the cosmic microwave background radiation, the faint afterglow of the Big Bang, a whisper from the birth of time itself. That one discovery confirmed Lemaitre's vision and transformed cosmology into a precision science. Now, we weren't just observing the stars, we were reading the universe's autobiography. In the decades that followed, space exploration pushed the frontier further. In 1957, Sputnik became the first human-made object to escape Earth's grip. In 1969, Neil Armstrong stepped onto the moon and uttered a phrase that echoed across generations. That's one small step for man, one giant leap for mankind. The Apollo missions revealed not just the surface of another world, but the fragility of our own pale blue that's suspended in darkness. The Voyager probes, launched in the late 2000s, carried humanity's voice into interstellar space and, decades later, sent back images of our solar system as a cosmic family portrait. As technology evolved, we launched space telescopes like Hubble, which unveiled the deep field, a haunting, humbling image of thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. We mapped the cosmic microwave background in detail with WIMAP and Planck satellites, revealing fluctuations in the early universe that seeded all future structure. These weren't just data points, they were fossils from the beginning, allowing us to reconstruct the first seconds of time, the birth of matter, and the unfolding of galaxies. All of this led to deeper questions. What is the shape of the universe? What is it made of? And perhaps most mysteriously, why is it expanding faster and faster? In 1998, 2 independent teams of astronomers discovered that the expansion of the universe is accelerating, a revelation that earned them the Nobel Prize and introduced a new cosmic player, dark energy, an unknown force that makes up 60% of the universe and pushes everything apart. Alongside it is dark matter, an invisible glue holding galaxies together, comprising another 60%. The matter we know, the stars, planets, people, makes up less than 20%. The universe, it turns out, is mostly made of things we can't see, don't understand, and can barely measure. And yet, from that uncertainty, we developed one of the most powerful concepts in cosmology, the observable universe. Because the speed of light is kilometers per second, we can only see as far as light has had time to travel since the Big Bang. about 13,8 billion years. But due to the universe's expansion, the actual radius of the observable universe is around 4,5 billion light-years in every direction, encompassing a spherical volume with over 6 trillion galaxies. Beyond that lies the unobservable regions too far for their light to have reached us, possibly infinite, or possibly curved back upon themselves in ways we don't yet grasp. The observable universe isn't a limit of space, but a limit of time. It defines the boundary of what we can know, not what exists. This distinction became central to modern cosmology, especially as we explored models like cosmic inflation, which suggests that in the first trillionth of a second, the universe expanded faster than the speed of light, ironing out irregularities and setting the stage for everything that followed. It also laid the foundation for the multiverse theory, the idea that our universe might be one bubble in a vast sea of universes, each with different physical constants, laws, and timelines. In this new cosmic vision, we are not central, not final, not even primary. We are one brief flare in an ocean of possible realities. And yet, from myth to mathematics, from Galileo's trembling hand sketching the moon's craters to James Webb revealing the earliest galaxies, our journey has never been about reducing the universe. To equations, it has been about elevating human consciousness to meet the scale of the cosmos. Our understanding evolved not just through data, but through courage. The courage to challenge ancient beliefs, to question our place in the stars, to peer into the darkness and say, what if? From the sacred skies of Mesopotamia to the particle accelerators beneath Switzerland, we've traced a line of curiosity that refuses to die. We now stand on the edge of even deeper mysteries: quantum gravity, black hole information paradoxes, and the terrifyingly beautiful idea that space and time themselves may be emergent, not fundamental. We are no longer asking whether Earth is the center of the universe. We are asking whether the universe is the center of anything at all. We are looking for patterns beyond patterns, seeking order not just in the stars, but in the very fabric of existence. And perhaps the most humbling realization is this: the more we learn, the more we understand how little we know. But in that humility lies our greatest strength, not the answers we found, but the questions we dare to keep asking. That is the real journey. That is the beating heart of cosmology. And in the silence between stars, in the gaps between galaxies, in the dark spaces between particles, we continue to listen. Why should we care about the universe, about black holes, quantum fluctuations, dark energy, cosmic microwave backgrounds, expansion rates, or multiverse theories? Because hidden within every scientific concept is something deeply personal, a mirror held up to the human soul. The universe isn't just out there, it's inside us. It's in our bones, in our blood, in the way we dream, wonder, grieve, and search. The atoms in our hands were forged in dying stars that exploded billions of years ago. The iron in your blood was once at the heart of a supernova. We don't just live in the universe, we are the universe, experiencing itself. And yet, when we look up at the night sky, we often feel small, fragile, and afraid. We stare into a vast darkness where galaxies spin silently and stars are born and die without anyone noticing. And in that silence, we confront something terrifying and beautiful: our own mortality. The void doesn't speak our language. It doesn't comfort us. It doesn't offer meaning. And still we keep looking. We build telescopes that stretch our vision billions of years into the past. We listen for signals in the static. We send golden records into space filled with our music, our greetings, our hope. Because in that infinite silence, we are desperate to know we're not alone, and not just in the sense of alien life, but in the sense of belonging to something greater than ourselves. There's a childlike wonder that lives in all of us, no matter our age. It's the voice that asked, where does the sky end? What's beyond the stars? Why am I here? Before we were old enough to know the words astrophysics or ontology. That wonder is sacred. And it's that same wonder that makes the idea of living inside a black hole not just an intellectual curiosity, but a spiritual earthquake. Because if true, it means everything we know, the stars, the laws of physics, Even time itself is not the totality of reality, but just a local illusion. It means there's more, much more. Maybe another universe beyond ours. Maybe a higher dimension where our laws don't apply. Maybe a grand cosmic loop where death becomes birth and endings become beginnings. We chase these questions not because we expect clean answers, but because the act of asking them makes us more alive. Every time you gaze into the night sky and feel that sudden ache in your chest, that overwhelming awareness of how big everything is, how small you are, how little time you truly have you're touching something real, that ache is the echo of your own cosmic roots calling you back home. It's easy to drown in daily life, school, work, bills, notifications, traffic, noise, but then something stops you. A meteor streaks across the sky. A photo from the James Webb Telescope shows ancient galaxies colliding in a ball of light. A documentary whispers that we're made of stardust. And suddenly, the veil lifts. Suddenly, you remember you're not just a person rushing from task to task. You're a brief arrangement of cosmic elements given the impossible chance to ask the universe where it came from. That chance is a miracle. And that's why we must care. Not because we'll find all the answers, but because in the search, we remember who we are. The fear we feel when contemplating the universe is the same fear we feel when facing anything vast and unknowable. Death, love, loss, time. But just like a black hole doesn't destroy information it transforms, either fear doesn't have to paralyze us. It can push us. It can pull us deeper. The void becomes a canvas, not a coffin. And the more we stare into it, the more we see ourselves reflected back, not as insignificant specks, but as witnesses to the rarest event in cosmic history, self-awareness. Think about that. For 13.8 billion years, the universe expanded, cooled, formed stars, planets, and molecules. Then, one day, a creature opened its eyes and said, "What am I?" That moment was sacred. And it's still happening right now, as you read this. You are part of the universe becoming conscious of itself. That's not poetry. That's physics. The electrons firing in your brain obey the same quantum rules as those inside a neutron star. The thoughts you think emerge from particles forged in stellar cores. When you cry, when you laugh, when you wonder if life has meaning, that's not weakness. That's the cosmos alive inside you. So when we ask, do we live inside a black hole? We're not just testing a theory, we're confronting the edge of what it means to exist. What is space? What is time? Are we trapped or are we free? Did we begin or have we always been? These aren't just equations, they're the deepest questions of being, wrapped in the language of cosmology. And the answers matter because they remind us that we are not just reacting to life, we are participating in a story far older and grander than we can imagine. The cosmic void terrifies us because it strips us down. There is no up or down in space, no center, no edge, no meaning except the one we create. But that's also its gift. The universe gives us the freedom to write our own story, to build, to explore, to feel. And in doing so, we become part of something eternal. Not eternal in the sense of infinite time, but eternal in the sense that we are a moment that matters. You will never be again. Not in this exact form, not with this exact mind, but you are here now, alive, thinking, asking, and that is enough. That is everything. People often say, "I'm just one person, what can I do?" But the truth is, every great discovery began with one person refusing to stop asking. Galileo in his tower, sketching the moon. Einstein scribbling in the quiet of a patent office. Hubble climbing a mountain to photograph the stars. Their curiosity changed history. Your curiosity could change the future. Maybe you're the one who will solve the next mystery. Or maybe you'll be the one to inspire someone else who will. Either way, the fire keeps burning. The human story continues. So the next time you feel lost, small, or afraid, look up. Let the stars remind you that you're part of something vast, not in a way that makes you meaningless, but in a way that makes your existence more meaningful. Because it's not just the universe we're exploring, it's ourselves. Every black hole we study, every galaxy we name, every signal we chase into the dark is a step closer to understanding who we are, why we're here, and what it means to be conscious in a cosmos that doesn't owe us answers but gives us the courage to seek them anyway. What if everything you've ever known, your memories, your relationships, your emotions, your entire lifetime exists inside the gravitational echo of something far greater than we can comprehend? What if this isn't the outside world, but the inside of something else? A cosmic womb, a hidden interior, a universe within, a universe. Stop for a moment and ask yourself, how do you know what real even means? Is reality what your eyes perceive? Or is it something deeper, filtered through layers of space, time, and consciousness? Do you believe your senses tell the truth, or are they only showing you what your brain has evolved to understand? If the laws of physics themselves are shaped by where we are and when we are, can we truly trust our understanding of the cosmos to be universal, or are we like fish trying to comprehend the ocean without ever breaching the surface? If our universe is expanding, what is it expanding into? If time had a beginning, what existed before it? If space is curved, could we be living in a closed loop with no outside at all? And if black holes don't destroy information, but transform it, then what does that say about the nature of life, death, and rebirth on a cosmic scale? These aren't just questions for physicists or philosophers. These are questions for you. Because the moment we realize we might be living inside a black hole, everything changes, not just the science, but the story, our story, the narrative of human existence, of progress, of purpose. Suddenly, we're not explorers looking out into space from a fixed point, we are passengers inside a much larger phenomenon, unaware of the true shape of our reality. This mystery matters because it challenges the very foundation of what we believe about existence. It demands humility, it demands curiosity, and most importantly, it demands participation. Because knowledge is no longer something to be passively consumed, it's something to be actively shaped. Right now, we are standing on the edge of a frontier not just of discovery, but of perception. The idea that our universe might reside inside a black hole invites us to rethink gravity, time, dimensions, and even consciousness itself. What does it mean to exist inside something we cannot escape? Does the boundary of our universe, the cosmic horizon, act like an event horizon, hiding a larger truth we're not equipped to see? What if black holes are not ends, but beginnings, gateways through which new universes are born? What if ours was born from the collapse of a massive star in another universe, and every black hole we observe is a seed of a new cosmos, branching off like a family tree of realities? This idea isn't just science fiction, it's grounded in equations, in models, in real theoretical frameworks like loop quantum gravity, torsion-based cosmology, and the holographic principle. But here's the real question. If it turns out to be true, how will that change you? Will it shake your faith or strengthen your wonder? Will it make life feel meaningless or unimaginably precious? Will it drive you deeper into science or further into mystery? The answers aren't obvious, but the conversation is essential. Because science doesn't advance in a vacuum. It evolves through questions, arguments, doubts, and the courage to challenge what we think we know. You don't have to be a physicist to participate. All you need is a mind willing to wander and a heart open to awe. So let me ask you directly, what do you think is beyond the edge of our universe? Do you believe in multiverses? Do you think time is linear, or could it be looping, folding, branching in ways we can't yet imagine? Do you think consciousness is bound to the brain, or is it connected to something deeper, woven into the very structure of the cosmos? What if we're not just physical beings living in a black hole, but informational beings, encoded in ways we've only begun to uncover? And if we are inside a black hole, what happens when we reach its center, or its edge? Or more unsettling, what if there is no edge at all? What if every answer leads to another layer of mystery? Would you still keep searching? Or would you stop and stare in wonder, grateful just to ask? These are the questions I want you to wrestle with, not because we need answers today, but because the act of questioning makes us more alive. It connects us. It pushes us forward. Every time you leave a comment, start a conversation, share your perspective, you're contributing to the most important human endeavor there is: the search for truth. Not the truth handed down from authority, but the truth we discover together through dialogue, skepticism, and imagination. So let's talk, let's debate, let's challenge each other. Not to be right, but to go deeper. What do you think happens inside a black hole? Do you think the Big Bang was really the beginning or just a transition from something else? Do you believe the universe is infinite or just very, very large? Could black holes be intelligent systems? Could they store or even process information? What if every time someone dies, their information doesn't vanish but becomes part of the boundary conditions of another universe? What if consciousness is a feature of the universe, not an accident of evolution? And if all of this is even partly true, what does it say about our responsibility as conscious beings, alive at this rare moment in cosmic time, able to reflect, question, and reach beyond ourselves? These aren't just fun thought experiments, they're doorways to creativity, to science, to art, to purpose. And in a world filled with noise, distraction, and disconnection, what could be more powerful than rediscovering wonder together? Maybe you'll leave this video with more questions than answers. That's okay. That's the point. But don't just scroll past engage. Share what this made you feel. Tell me what you believe. Challenge the theory. Ask your own what if. Because the real revolution won't come from scientists alone, it'll come from you. From dreamers, artists, students, skeptics, and storytellers daring to step into the unknown and say, let's explore this together. This mystery affects everything. It affects how we define life, how we define death, how we define reality itself. It redefines distance, time, scale, and meaning. And it forces us to face the deepest truth of all. We are not observers of the universe, we are participants in it. So the next time someone tells you that physics is boring or that space is just out there, remind them, it's not out there, it's in here. It's in the questions we ask, in the stories we tell, in the connections we make when we realize we are all part of a cosmic narrative still unfolding, page by page, across dimensions we can't yet see. Don't wait for the final answer. Be part of the conversation. Because this is how it starts. One question, one comment, one spark, and then the universe answers back. Step outside the boundaries of Earth, past the clouds and the ozone and the satellites we've hurled into low orbit, and you enter a silence so complete it swallows sound before it's born a cold. Airless vacuum stretching in every direction, not empty but pregnant with energy, ancient light, and invisible forces. Space is not black, it's a deep canvas stained with relic photons, dust clouds, and the glimmering bones of dead stars. Our solar system is a small flickering campfire surrounded by a forest of giants. The planets hum quietly in their orbits, tethered to the sun by gravity's invisible thread. But even our star, massive and dominant, is just one of hundreds of billions orbiting within the Milky Way, a swirling spiral galaxy over Sata, Nola light-years across, its arms coiled like cosmic smoke frozen in motion. Each point of light you see in the night sky is a sun, many orbited by planets, many older than Earth, many already gone, their light just now reaching us. And yet, the Milky Way is only a speck within the local group, a tiny neighborhood of galaxies caught in mutual gravitational embrace, drifting toward the Virgo cluster, which itself is part of the Laniakea supercluster, an enormous gravitational basin of galaxies interconnected like neurons in a brain far beyond our comprehension. These clusters form filaments, tendrils of light and matter stretching for hundreds of millions of light years, wrapping around vast cosmic voids, some say dark regions of almost nothing, where entire galaxies are absent. These voids are not empty by mistake. They are sculpted by the gravitational pull of dark matter, an invisible scaffolding 5 times more abundant than the ordinary matter we see. We don't know what it's made of. We can't touch it, can't see it, but we know it's there because without it, galaxies would fly apart, cosmic structures would collapse, and the universe as we know it would never have formed. Beyond that, everywhere, is the strange push of dark energy, a repulsive force causing the very fabric of space-time to expand faster and faster, stretching galaxies away from each other, accelerating the loneliness of the cosmos. It's like being inside a balloon inflating, endlessly. Not into air, but into more space itself. And at the largest scales, the universe reveals a structure so vast and elegant it defies language. The cosmic web, a lace of matter, galaxies, and black holes woven together by physics and time, an architecture of creation born from quantum fluctuations in the earliest moments of existence. This isn't science fiction. This is the reality scientists like Stephen Hawking, Alan Guth, Kip Thorne, and Andre Linde have spent their lives trying to understand. These are not dreamers, they are explorers of the mind, building equations that describe wormholes, inflation, multiverses, and the geometry of space-time itself. Hawking gave us the bold idea that black holes are not eternal, but evaporate slowly, releasing information taking the foundations of entropy and the second law of thermodynamics. Guth gave us cosmic inflation, the theory that the universe expanded faster than light in a fraction of a second, smoothing out irregularities and seeding the galaxies. Linde took it further with chaotic inflation, suggesting an endless sea of bubble universes forming from quantum fields in constant flux. Thorne explored the engineering of space-time itself, wormholes, time travel, and the terrifying consequences of singularities, helping even Hollywood, in Interstellar, visualize what a real black hole might look like. Its light bent into a glowing hollow beam, gravity so strong it twists the very concept of direction. These aren't just equations, they're windows into a universe more alien than any fiction, yet utterly, breathtakingly real. Black holes themselves are the great sculptors of cosmic drama. Born from the collapse of massive stars, they warp space and time into lethal traps. But they may also birth new universes, depending on how singularities are treated in quantum gravity. They sit at the centers of galaxies, including our own, the supermassive black hole Sagittarius A, shaping galactic evolution, powering quasars, and devouring matter at relativistic speeds. Some black holes spin so fast that their rotational energy could theoretically be harvested. Others merge in violent dances, sending ripples, gravitational waves through the fabric of reality, detected by instruments like LIGO and Virgo, confirming Einstein's predictions a century later and opening a new sense through which to hear the universe. But for all the noise of explosions, orbits, and particle collisions, the dominant tone of the cosmos is silence. And yet, it speaks. In microwave whispers from the Big Bang, we hear its birth 3,8 billion years ago, not in an explosion, but in an expansion, everywhere at once. From an unimaginably hot and dense origin, the universe cooled and expanded, forming hydrogen, then stars, then carbon, then life. And now, it says itself through us. We are made of the same stuff as galaxies: carbon, oxygen, nitrogen, iron, assembled in such a way that we can ask questions no other species on Earth has dared to ask. What am I? Where did I come from? Why is there something rather than nothing? We built telescopes not because we wanted pretty pictures, but because we're desperate to see further, to trace light back to its source, to understand where it came from and what came before. The James Webb Space Telescope now peers so deep into the early universe that it may capture the light from the first star's population, 3 stars, massive and short-lived, born in a universe barely formed, their death seeding everything we now know. As we move deeper into the Coxycumenteix's century, scientists like Sara Seager, Brian Greene, Sean Carroll, and Katie Mack are carrying the torch, studying the multiverse, the fate of the cosmos, the relationship between consciousness and entropy. The frontier is not a place. It is a question. And the deeper we go, the more we realize we are not studying the universe from the outside, we are within it, embedded, entangled, part of the very process we're trying to understand. Every cosmic structure, from the rotation of galaxies to the spin of particles, obeys a rhythm, and somehow, miraculously, our thoughts are in tune with it. The atmosphere of the cosmos is not only physical, it's philosophical. It is heavy with mystery and alive with meaning. We gaze into black holes not only to learn about space-time, but because we want to know if everything ends or transforms. We study galaxies to learn how matter organizes, but we also want to understand if complexity, life, and intelligence are inevitably rare miracles. The night sky is not silent. It's a cathedral. It's a question mark etched into the dark. It's a mirror reflecting what we are: fragile, curious, temporary, and yet eternal in our desire to know. Away is the proper response to this reality, not fear, not apathy, awe. Because when you realize that you're standing on a planet orbiting a star that's drifting in, a galaxy that's hurtling through an expanding universe, and you're conscious of it, that's not just knowledge. That's a gift. You are a moment of awareness in an ocean of entropy. You are a flare of meaning in a sea of uncertainty. You are part of a story still being written in particles, in stars, in thought. So breathe it in. Look up. Feel the chill of cosmic perspective wrap around your mind like the vacuum beyond Earth's skin. You're not alone in wondering. You're not foolish for dreaming. You're part of a species that has gone from firelight to satellites, from myths to quantum fields, from stone tools to gravitational wave detectors. And we're just getting started. The atmosphere of the cosmos is not empty. It's full of questions, possibilities, and light that has traveled billions of years just to touch your eyes. The universe is not a void. It's a stage, and you're on it. Even as we chase the edges of the universe with machines of staggering precision and minds trained to slice reality into equations, a haunting truth begins to emerge from the shadows of our own ambition. We may never find the true edge, not because we lack effort or intelligence, but because the edge itself might not exist in the way we imagine it, or worse, because it is hidden by the very fabric of space and time we're trying to understand. From the earliest days of cosmology, we've been warned whispers of paradoxes buried inside our brightest ideas, cracks in the surface of scientific certainty that hint at something deeper and more elusive. Einstein's theory of general relativity, the cornerstone of modern physics, tells us how gravity bends space and time, how massive objects warp the world around them like weights on a trampoline. But it also predicts the existence of singularities regions where these equations break down entirely, where density becomes infinite and time ceases to make sense. These singularities appear at the heart of black holes and, according to the Big Bang model, at the beginning of our universe. Yet singularities are not answers, they are boundaries where logic collapses. They are the universe's way of saying, you can't go any further with this map. They are not places, they are warnings. The more we try to trace the universe back to its first moment, the more our mathematics unravels into infinities, undefined quantities, and mysteries that mock our deepest assumptions. Quantum mechanics, which governs the smallest scales of reality, adds its own kind of chaos. Unlike classical physics, where cause leads predictably to effect, quantum systems are governed by probabilities. A particle doesn't exist in one place until it's observed. It exists in a cloud of possibilities. The closer we look, the fuzzier everything becomes. And when we try to merge quantum theory with general relativity, when we ask how gravity behaves at the smallest scales, like inside a black hole or before the Big Bang, we get contradictions, paradoxes, dead ends. Our best theories, the ones we trust with satellites and supercollidors, refuse to speak to each other at the moment we need them most. That failure isn't just technical, it's existential, because it means there may be a limit not only to what we can observe, but to what we can know. Our telescopes, no matter how advanced, are prisoners of light. And light, bound by the speed limit of 660 kilometers per second, can only tell us about regions that have had time to reach us since the birth of the universe. That's the observable universe, a bubble, with a radius of about 4,6 billion light-years. But beyond that, we have no access. Not because there's nothing there, but because the light from those places hasn't had time to reach us and possibly never will. The expansion of space isn't just carrying galaxies away, it's accelerating them beyond the reach of light itself. There are regions of the cosmos receding from us faster than light can travel, creating a horizon not unlike the event horizon of a black hole, a boundary we can never cross. And inside our universe, at the quantum level, particles routinely diffuse intuition, appearing and disappearing from existence in what we call virtual interactions. Even the vacuum isn't empty, it boils with energy, with possibility. Space itself, it turns out, is dynamic and unstable, subject to fluctuations that could, in theory, spawn new universes entirely. And that leads us to the greatest riddle of all. What if our universe is not everything, but just one bubble in an endless foam of creation? What if the Big Bang was not the beginning, but merely our beginning a local explosion in an eternal multiverse? That's the promise of inflationary theory, string landscapes, and eternal inflation, that universes are born all the time, expanding into their own space-times, forever cut off from each other. But if that's true, we can never confirm it not unless there's a tear in the cosmic fabric, a collision between universes, a detectable scar in the microwave background. And even then, how do we distinguish what's real from what's mathematical elegance? Our instruments are limited. Our bodies are limited. Our brains evolved not to decode the universe, but to survive on a Paleolithic savanna, to recognize faces and find food and flee predators. And yet here we are, trying to decode an Eliatoista billion-year-old puzzle using tools that barely scrape its surface. Every time we think we've solved it, every time we glimpse a theory of everything, a new contradiction appears, like a trick of the light. Dark matter refuses to reveal its composition. Dark energy defies any consistent model. The universe accelerates, and no one knows why. Black holes swallow information, but quantum mechanics says information cannot be destroyed. So which is wrong? Or are we both right and wrong in ways we don't yet understand? And now, some physicists propose that we might live inside a black hole ourselves, that our universe, expanding from a singularity, bounded by a cosmic horizon, governed by entropy and geometry, resembles not an explosion into empty space, but the internal structure of a black hole birthed from another universe's collapse. That's a theory both elegant and disturbing, because if true, it means our observable reality is bounded in ways we can't escape. It means the outside the true universe beyond our own might be forever hidden from view, not by distance, but by geometry. And more terrifyingly, it might mean we're living in a simulation, a projection, a mathematical structure with no access to its origin. The holographic principle suggests that all the information inside a region of space can be encoded on its boundary. If that's true, then everything you've ever known, your memories, your sensations, your thoughts, could be part of a cosmic computation running on the edge of reality. But how would we know? What could we test? What could we observe that isn't already filtered through the limitations of our senses, our technology, our perspective? This is the heart of the conflict. Not that we are ignorant, but that the universe may be constructed to deny us certain knowledge, like a book that harasses its final chapter, like a puzzle with pieces that vanish as you approach. Every discovery we make opens 10 more questions. Every step forward feels like reaching the edge, only to find it moving again, retreating like a horizon across a dark ocean. And the deeper we go, the more uncertain the ground beneath us becomes. We speak of time, but we don't know what it is. We speak of space, but we don't know what it's made of. We assume causality, but quantum entanglement defies it. We rely on the arrow of time, but our laws of physics are time-symmetric. We live, we think, we feel, but we don't know if consciousness is fundamental, emergent, or even relevant to the universe at large. And still, we search. We build larger collidors, deeper space telescopes, more precise atomic clocks. We scan the skies for anomalies, patterns, and signals. But behind every answer is a shadow, a whisper that says, "You're still inside the maze." The edge we seek may not be spatial, it may not be temporal, it may be conceptual, a boundary of understanding, of cognitive reach. The Greeks once believed in the apieiron, the infinite, unknowable void beyond all things. We've dressed it up with equations, mapped it with satellites, framed it in the language of quantum fields and Planck lengths, but we're still facing the same abyss. And what makes this conflict so powerful, so personal, is that it speaks to something primal in us. The fear that the universe is not only vast, but unknowable. That there is a ceiling to comprehension. That we may be guests in a reality whose rules were not designed for our discovery. That our questions, no matter how precise, might never receive an answer. And yet we keep asking. Because giving up the search would be worse than not finding the edge. The true tragedy would not be that the universe is unknowable. The true tragedy would be that we stopped trying, that we stopped wondering, that we surrendered to the mystery rather than dancing with it. So we go on, with questions as fuel, with paradox as compass, with the silence of the stars as both warning and invitation. And in that silence, we begin to understand. Perhaps the edge is not a place to find, but a pressure to feel the tension between what is and what could be. The conflict isn't out there. It's within us, and it's just beginning. There is a war unfolding beneath the quiet brilliance of the stars, not of weapons or armies, but of minds, ideas, and the very fabric of understanding, a silent, tireless conflict, fought by physicists, cosmologists, mathematicians, and dreamers, all wrestling with a question so massive it fractures even the sharpest intellect. Does the universe have an edge, or is it infinite? Is there a boundary we'll someday reach? A final wall where time breaks, where space runs out? Or are we trapped in an endless sea of existence, with no direction home? For over a century, the greatest thinkers on Earth have tried to map the shape of reality itself, and every answer has opened a deeper divide. The observable universe, limited by the speed of light and the age of time, shows us a spherical bubble of galaxies stretching nilyakumintakus pilkuvisi billion light-years in all directions. That's what we see. But what lies beyond ITIF? Anything that remains wrapped in darkness. Some models, based on Einstein's general relativity, suggest the universe is finite, but unbounded, like the surface of a sphere in higher dimensions. You can travel forever without reaching an edge, yet space is still closed in on itself. Others argue the universe is truly infinite, stretching endlessly in all directions with no beginning and no end. But infinity is a dangerous word in physics. It breaks equations. It defies measurement. And in the face of quantum mechanics, it feels like cheating, a placeholder for our ignorance. So cosmologists split into camps, each armed with models and math, and the battle lines are drawn. On one side, those who believe the universe is infinity, an endless expanse, birthed from a single Big Bang that continues forever. On the other, those who argue for a bounded cosmos, shaped by hidden curvature, wrapped around itself, or enclosed within something even larger, like the interior of a black hole. But that's only the surface. Deeper still, the fight intensifies between theory and observation. What we can measure often contradicts what our theories predict. The Standard Model of Cosmology, LCDM, assumes dark energy is a constant force pushing space apart, yet no one knows what it is. We infer its presence from the way galaxies accelerate away from each other, but we can't detect it directly. Dark matter, too, is only seen through its gravitational fingerprint. And string theory, which promises a grand unification of all forces, predicts a vast landscape of possible universes, but it has not produced a single testable prediction in decades. So who do we trust, the data, which is incomplete, or the theory, which is beautiful, but unverified? This is where the conflict becomes emotional, because science, for all its logic, is still carried by humans with biases, with hopes, with reputations built on being right. Some physicists believe in elegance, in mathematical beauty, in symmetry and harmony as if the universe should make sense. Others follow the raw data wherever it leads, even if it breaks everything we thought we knew. And between them is a battlefield of failed experiments, conflicting measurements, and philosophical tension. The idea of an edge of a place, where the universe ends, is not just physical, it's political, it's personal. It affects funding, careers, the direction of decades of research. And beneath it all is a deeper, quieter struggle. The fear that the edge may never be found, not because it isn't there, but because we are not equipped to recognize it. Every model has its limits. The Big Bang Theory, for all its power, breaks down at T equals null. Quantum mechanics cannot explain gravity. Relativity cannot explain the quantum vacuum. And the theories that try to bridge them, like loop quantum gravity, causal dynamical triangulations, or emergent spacetime, remain unfinished, incomplete, elegant ghosts with no experimental anchor. Even the idea of time itself is under attack. Some theories suggest time is an illusion, that all moments exist simultaneously, and our perception of flow is merely a trick of entropy. Others argue space and time are emergent, born from entanglement and information, not fundamental at all. So if space is emergent, how can it have an edge? If time is an illusion, how can anything begin? These aren't just semantic arguments, they're tectonic rifts in the foundation of physics. And as each new observation comes in from the James Webb Space Telescope, from LIGO's gravitational waves, from Planck's CMB maps, it brings more tension, not less. Webb has shown us ancient galaxies forming faster than theory allows. Gravitational waves confirm black hole mergers, but raise new questions about what lies at their cores. The cosmic microwave background remains smooth where we expected chaos, quiet where we expected noise, and anomalies, cold spots, axis alignments, and tensions in the Hubble constant suggest cracks in the Standard Model. Cosmologists debate with passion and precision, some clinging to inflationary models that explain the early universe with a burst of exponential expansion, others rejecting it entirely in favor of bouncing cosmologies or ekpyrotic scenarios that propose a universe born from the collision of higher dimensional brains. The stakes are high. Each theory comes with implications about the edge, whether it exists, whether it's reachable, whether it's even real. And at the heart of this is a single, burning contradiction. If the universe has an edge, what lies beyond it? And if it doesn't, how can anything finite contain infinite complexity? This is the clash between the tidy world of theory and the messy, uncertain world of observation. Between the desire for a complete equation and the humility of unknowing. Between those who say the universe must make sense and those who say it doesn't owe us anything. And the deeper we go, the more personal it becomes. Because behind every theory is a human being trying to answer the oldest questions. Where are we? What are we? Why does anything exist at all? This isn't just science. It's soul-searching through numbers. It's the act of wonder dressed in equations. It's the conflict between logic and longing, between what we can prove and what we feel must be true. Some scientists dream of a final theory, a theory of everything, that will explain the universe's birth, structure, and fate in one elegant framework. Others believe such a theory may never come, that we are limited by our cognitive architecture, our dimensional blindness, our inability to ask the right questions. But everyone agrees on one thing. The universe is under no obligation to reveal itself on our terms. We are intruders into its logic, visitors in a world written in a language we've only just begun to learn. The edge, if it exists, may not be physical at all. It may be epistemic, a limit of knowledge, or it may be technological, a place we cannot reach, even in theory. Or it may be something far stranger, a horizon built by the universe to protect itself from our understanding. A paradox we can approach but never resolve. And yet, we continue, we theorize, we simulate. We launch telescopes into the void. We gather in labs and lectures, in silence and debate, pushing against the darkness with chalk and code. The tension drives us, the conflict fuels us. Because in that conflict between finity and infinite, between seen and unseen, between now and forever, we find our purpose. Not to conquer the cosmos, but to reach for it anyway. What if the universe has no edge? What if all our searching, all our equations, all our observatory is scanning deep time for a boundary line come back empty? Not because we failed, but because there was never a boundary to begin with. What if space doesn't end, but loops or stretches or flows infinitely, curving in ways we cannot visualize, unfolding in higher dimensions we can't perceive? If the universe has no edge, then we are trapped in a reality without perimeter, a cosmic paradox where distance becomes meaningless, and the very idea of outside dissolves like mist under a burning question. Where are we, really? The consequences are profound, not just for physics but for the human experience. A boundless universe breaks more than mathematical expectations. It breaks the idea that things are knowable, containable, that questions will eventually lead to closure. Suddenly, the cosmos becomes a labyrinth with no center, no exit, no final truth waiting at the end of a long corridor of discovery. For physicists, this forces a reckoning with the limits of our theories. General relativity assumes a smooth, predictable geometry of space-time, but it falters under quantum pressure. Quantum mechanics gives us probabilities, not certainties, and yet cannot explain gravity. These two pillars of modern physics, both spectacularly accurate in their domains, refuse to reconcile. They circle each other like binary stars, each powerful, each beautiful, yet incapable of becoming one. If the universe is infinite, the models that attempt to describe it must contend with infinities of energy, of entropy, of information. But physics dispieces infinity. It signals a breakdown, a place where the math spirals out of control and our conceptual framework begins to stutter like an old machine pushed too far. If the universe is truly unbounded, we can no longer rely on boundary conditions to solve our equations. We must rewrite our understanding of causality, locality, and perhaps even the nature of existence itself. Infinite space raises another harrowing specter: infinite copies. In a truly infinite universe, the laws of probability demand that every possible configuration of matter not only exists, but exists an infinite number of times. That means there are other versions of you living, dying, making different choices in regions of space, so distant that light from there will never reach us. You are unique only within the observable bubble. Beyond that, you are echoed, repeated, lost in an eternal recursion of matter and thought. That thought haunts philosophy. Because if everything happens somewhere, what does morality mean? What does free will mean? If your life, in every form, is already out there, then what are you, except a single strand in a cosmic braid of infinite variations? And yet, if the universe is infinity, and yet still expanding, that means even infinity is not static. The volume of existence is growing. New regions are becoming real. Time is not only flowing, it is building reality as it goes. But if the universe is finite and has no edge, like the surface of a sphere in higher dimensions, then we're still trapped looping forever without exit, like ants crawling on a balloon with no sense of above or below. Either way, edge or no edge, we are surrounded by mystery. But mystery is not neutral. It demands response. Without an edge, there is no outside observer, no from the outside perspective, no cosmic vantage point where we could step back and view the whole. We are stuck inside the story, unable to read the final page, forced to interpret the plot from within the narrative. And that changes everything. It means that science is not only about discovery, but about limitation. It means that our theories will always be based on partial truths, local realities that may not scale beyond our observational horizon. The tension between finite measurement and infinite theory cracks the foundation of empirical science. It means we need new physics, not just more precise instruments or stronger telescopes, but a new conceptual revolution. Just as Einstein redefined gravity, just as quantum mechanics shattered classical determinism, we need a new language that fuses the finite and the infinite, the measurable and the unknowable. Perhaps space-time is not fundamental. Perhaps particles are not truly objects, but vibrations in a deeper field. Perhaps the edge we search for isn't spatial at all, it's informational. The holographic principle hints that our Colmead universe may be encoded on a Coxeid surface, like a cosmic movie projected into our experience. If that's true, then the edge isn't something we travel toward, it's something that encodes us from the outside. We are the shadows, but even that model carries conflict. What encodes the encoder? What projects the projector? The more layers we peel away, the more the core eludes us. Philosophers have long warned us of this, that beyond every mystery lies another. That meaning itself may be emergent, just like space, time, and matter. So what then? Do we give up? Do we accept the edge as unreachable, or unreal, or irrelevant? No, because the absence of an edge does not mean the absence of direction. We may never find the boundary, but we can chart the inside. We can discover structure, curvature, relationships. We can still map the known, even if the unknown stretches forever. And perhaps that's the point. The universe is not a puzzle with a single solution. It's a mirror, showing us our limitations and our longing. The conflict between edge and no edge, between finite and infinite, is not just theoretical, it's emotional. Because humans crave closure. We want endings. We want stories to have resolution. But the universe may not be a story, it may be a song, repeating, evolving, fractal in nature, infinite in variation. And like music, it may never end. That doesn't diminish its beauty. It enhances it. Because if there is no final chapter, then every moment matters, every observation, every theory, every wonder. That is what keeps cosmologists awake at night, not just the fear of being wrong, but the fear of never knowing, of chasing shadows across eternity, of running simulations that never converge, of mapping a terrain that keeps expanding as we measure it. And yet, we continue. We collide particles. We chart distant galaxies. We argue. We revise. We imagine. We search for laws that can contain the uncontainable. And perhaps one day we will find them not because we reached the edge, but because we changed our definition of what an edge is. Maybe the edge is the boundary between ignorance and knowledge. Maybe the edge is us, the point where the universe becomes conscious of itself. In the end, the consequences of this conflict go far beyond physics. They reach into the core of what it means to be human, to wonder, to strive, to build cathedrals of knowledge in a universe that may never give us permission to see the whole. But still, we look, because the alternative is silence. And silence is not an answer, it's a void. And the void, no matter how vast, cannot defeat a species that dare us to ask what lies beyond. There comes a moment in every great story when the protagonist glimpses a truth so powerful, so disruptive, that everything changes, and for humanity's journey through the stars, that moment came not in fire or revelation, but in silence, data, and a strange acceleration no one could explain. For centuries, we believed the universe was slowing down, its expansion dragged by gravity, destined to collapse into itself or stretch into cold stillness. That was the narrative: expansion, balance, decline. But then, at the end of the Cax-Kumanteth century, two independent teams of astronomers led by Saul Perlmutter, Brian Schmidt, and Adam Rees looked deep into the night using distant Type Ia supernovae as cosmic mile markers, expecting to confirm a universe decelerating under its own weight. Instead, they found something no one anticipated. The supernovae were dimmer than they should have been, not because they were smaller, but because they were farther away, farther than the models allowed. The universe wasn't just expanding, it was accelerating. That one revelation detonated across cosmology like a bomb. It rewrote the laws of cosmic fate. It forced the reintroduction of a forgotten term, Einstein's cosmological constant, which he had once called his greatest blunder, and with it came a mystery more profound than any we had yet encountered: dark energy. An invisible pressure, smooth and omnipresent, woven into the very fabric of space itself. It doesn't pull, it pushes, not from outside, but from within. The more space there is, the more dark energy manifests, and the more it accelerates the expansion, tearing galaxies away from each other like stars drifting in a dying fire. Today, we believe dark energy makes up 96% of the total energy content of the universe. Yet we don't know what it is. A vacuum energy? A scalar field? A property of space-time geometry itself? It is the most dominant force in the cosmos and the least understood. And with it, the tone of our journey changed. This was no longer a tale of exploration alone. It became a confrontation with limits of observation, limits of interpretation, and limits of existence itself. Because if dark energy continues to dominate, it implies a future where galaxies accelerate beyond our horizon, where light from distant stars will never reach us, where every point in the universe becomes increasingly isolated. A future of loneliness, of cosmic silence. But in that silence, new questions screamed to be answered. And we responded not with surrender, but with innovation. We built better instruments. We pushed our eyes farther. The Hubble Space Telescope, launched in 2019, gave us the clearest view of deep space we had ever seen. It peered into time itself, capturing the Hubble Deep Field, a patch of darkness revealed to be a forest of ancient galaxies, each a world of its own. Then came WIMAP, and later Planck, which mapped the cosmic microwave background, the afterglow of the Big Bang, with exquisite precision, allowing us to measure the age, shape, and composition of the universe like never before. These missions confirmed the presence of dark energy, dark matter, and a nearly flat spatial geometry, supporting the LCDM model, the standard framework of modern cosmology. But they also revealed tensions. The expansion rate measured from the early universe didn't match the rate we see today, discrepancy called the Hubble tension, which continues to puzzle and provoke the field. Then came gravitational wave observatories LIGO and Virgo, which in 2015 detected the ripples from a collision of black holes over 1 billion light-years away. For the first time, we weren't just seeing the universe, we were hearing it. Gravitational waves opened an entirely new window into cosmic events that leave no light behind, giving us a way to test relativity in extreme conditions and to explore the darkest corners of existence. And now, in the present moment, the James Webb Space Telescope is rewriting our maps again. Peering farther and deeper than any instrument before it, Webb has captured light from galaxies born when the universe was just a few 100 million years old, shockingly mature, bright, and massive for their age. These galaxies defy predictions. They form stars too quickly. They show structure too early. They whisper that something is wronger, perhaps beautifully incomplete in our current understanding of cosmic evolution. And Webb's infrared vision has also revealed astonishing details about exoplanets, gas clouds, star nurseries, and the chemistry of deep space, hinting at new rules of formation, new compositions, and maybe, one day, even signs of life. Every advancement in technology has pushed the boundary of what we thought possible, and with each push, the universe pushed back. Our particle colliders, like the Large Hadron Collider, confirmed the existence of the Higgs boson, completing the standard model of particle physics, but also raising questions about why the Higgs mass is so finely tuned, and why our vacuum is stable at all. Some now suggest that our universe sits on the edge of a deeper energy landscape, that it could decay into a lower energy state, obliterating everything in a blink. Others explore the quantum foam, the Planck-scale storm at the heart of space-time, where virtual particles flicker into and out of existence, and where the known laws break down. These are not sci-fi fantasies, they are real frontiers, debated in conferences, tested in labs, and simulated on quantum computers being developed today. And threading through all of this is the same question: where is the edge? The edge of knowledge, the edge of observation, the edge of reality itself. Dark energy doesn't just stretch. Space, it stretches meaning. Because if it keeps accelerating, the universe may face a big freeze, where all matter decays, all stars die, and entropy reaches its maximum. Or a big rip, where dark energy tears galaxies, stars, and even atoms apart, ending existence not with a bang, but a scream of unmaking. Or maybe a bounce, where quantum gravity triggers a new beginning after this one fades. But none of these answers are final. They are all contingent on future data, future theories, future minds bold enough to look beyond what the past made sacred. This is the turning point, where the old models falter and new physics must rise, where even constants like the speed of light or the fine structure constant are examined under the microscope of cosmological evolution, where the role of consciousness is whispered in the same breath as entropy, where the edge may not be a place, but a perspective, a shift in how we define the universe, not as a static thing, but as a process, unfolding, probabilistic, and strange. And in this process, humanity is not a passive observer. We are part of the unfolding. Our minds, our instruments, our languageal expressions of the universe attempting to understand itself. The photons that began their journey billions of years ago now end in our telescopes, our retinas, our thoughts. That is not coincidence, that is connection. And so the turning point is not just scientific, it is emotional, philosophical, existential. It is the moment we realize the story of the universe is not a straight line, but a spiral, and that every revelation is not an answer, but an invitation to go deeper, to question harder, to imagine further. We once believed Earth was the center, then the sun, then the galaxy, then the visible universe. Now we wonder if there is a center at all, or if meaning, like space, expands endlessly. That's the gift of this moment, not certainty, but possibility. A turning point where we do not close the book, but turn the page, and what we find next will change everything again. What if the reason we can't find the edge of the universe is not because it's too far, too faint, or too hidden, but because the very way we're looking is wrong? What if we've spent decades staring outward, building bigger telescopes, measuring faster redshifts, drawing maps on maps of space, and all this time the real breakthrough was not in distance, but in direction? What if the truth about the cosmos doesn't lie in reaching the farthest galaxy, but in reframing the question itself? Because in physics, as in life, there are moments when progress isn't made by going forward, but by turning around, rethinking, reinterpreting. And that's exactly what some of the most radical and respected scientific theories are now doing. They're telling us that the universe may not be what it appears, that space-time and even matter may not be fundamental, that reality as we experience it could be a projection and emergent property, not the root, but the result of something deeper. This is the great shift in perspective, and it begins with a paradox: black holes. These mysterious objects, predicted by Einstein, confirmed by observation, and photographed in haunting glory by the Event Horizon Telescope, don't just warp space, they warp understanding. According to general relativity, all matter falling into a black hole is crushed into a singularity, an infinitely dense point where physics breaks down. But quantum mechanics insists information cannot be destroyed. That's not a suggestion, it's a law. And when Hawking proposed that black holes slowly evaporate via radiation, he sparked the information paradox, a contradiction at the heart of our most trusted theories. Where does the information go? Does it vanish with the black hole? If so, quantum mechanics fails. If not, relativity fails. The conflict was unsustainable, and from this tension emerged a bold idea. What if the information isn't lost, but encoded on the event horizon itself? What if the surface of the black hole stores all the data about what fell in like a hard drive at the boundary of reality? This led to the holographic principle, a mind-bending theory first suggested by Gerard Hooft and refined by Leonard Susskind, which says that everything inside a region of space can be described by data on its boundary. That is, our entire three-dimensional universe may be the projection of two-dimensional information encoded at the edge like a hologram, where depth is an illusion born of encoded surface light. It's not just metaphor, it's math. And in 1967, theoretical physicist Juan Maldacena discovered a version of this in action, the ADS-CFT correspondencia duality that equates a gravitational theory in a higher dimensional bulk space with a quantum field theory on its lower dimensional boundary. It was a moment of cosmic judo flipping the very architecture of understanding. Suddenly, gravity and quantum mechanics could speak. Suddenly, the idea of space and time is emergent, not built in, but born from entanglement, from information, from quantum structure became viable. And that shook the foundations of physics to the core. Because if space and time are not fundamental, then the universe isn't a stage at all, it's an experience, a process, a computation. And maybe there is no edge, because there is no underlying space-time to reach. Just a quantum network expressing itself as geometry. Just patterns of entanglement giving rise to distance. In this new perspective, where becomes less important than how, and this brings quantum mechanics into the very heart of cosmic structure. In standard cosmology, the universe began as a densy, hot singularity. But what triggered the Big Bang? What set the initial conditions? Classical physics has no answer, but quantum physics might. In some interpretations, the universe is not a singular event, but a quantum fluctuation of many, arising spontaneously from a deeper quantum field. In this view, time itself may be an emergent illusion, born from decoherence, the process by which quantum possibilities collapse into classical realities. It means the arrow of time, the forward flow we experience, could be a trick of entropy, not a universal law. It means the beginning of the universe wasn't a start, but a transition from nothingness, not into something, but into structure. And perhaps that structure didn't unfold in space, it created space. Already, new theories like loop quantum gravity, causal set theory, and spin networks suggest that space-time might be granular, built from tiny quanta of geometry, stitched together not by force, but by relationship. In these models, the universe is not a container, it's a graph, a web, a set of informational connections. And just like consciousness emerges from neurons firing in patterns, space may emerge from the way quantum bits relate to each other. This changes everything. It means distance is a matter of entanglement. It means location is a product of informational similarity. It means reality is not made of stuff, but of code. And if that's true, then we must stop asking, what lies beyond the universe? And instead ask, what kind of computation gives rise to the universe as we experience it? It's not mysticism, it's math, and it's gaining ground. Theoretical physicists like Carlo Rovelli, Fotini Marco Polo, Lee Smolin, Sean Carroll, and others are all exploring models where time, space, and even causality emerge from a deeper substrate. And in the lab, quantum computing is beginning to demonstrate that reality is not as fixed as we thought, that information and observation change the outcome. Quantum entanglement, dismissed as spooky action at a distance, is now being weaponized to build new technology, probe black holes, and rethink the nature of connection. And all of this leads to a radical conclusion. The problem isn't that we can't find the edge of the universe. The problem is assuming there should be one. Just like early cartographers believed the world had a physical edge, just like we once believed the heavens rotated around Earth, perhaps we're asking the wrong question entirely. Perhaps the edge isn't out there. Perhaps it's in our thinking. And when we change the question, when we flip the map, when we stop demanding the universe conform to our expectations, everything opens. In this new view, the universe isn't a place you travel through. It's a process you participate in. It's not static, it's interactive. It responds to observation. It reshapes around information. It evolves through feedback loops, complexity, and emergence. And just as a story is more than ink on a page, the cosmos is more than particles in space. It is meaning, unfolding. It is context, breathing. It is code, dreaming itself awake. And suddenly, we begin to understand, maybe we are not on the outside of the mystery, looking in. Maybe we are the mystery, looking at itself from the inside. Maybe there is no beyond, because there is no outside, just higher levels of recursion, just deeper states of structure, just different ways of seeing. That is the shift, not just in perspective, but in identity. We are not merely stardust. We are patterned stardust, observing itself. We are not lost in the universe. We are the universe, learning how to ask better questions. And those questions are our telescope now. Because maybe the final revolution won't be technological. Maybe it will be philosophical. The moment we realize that the cosmos isn't about edges, it's about relationships. Not about answers, but about refinement. Not about finding the limits of space, but about understanding the space between limits. And in that space, we will find something greater than knowledge. We will find wonder. Just when it seemed we were beginning to understand the architecture of the universe, its expansion, its birth, its dark components, a new and unrelenting twist emerged, as if reality itself had been quietly withholding its most astonishing secrets, waiting for us to reach the edge of comprehension before pulling the floor out from under our certainty. The data didn't break our theories, it twisted them. Galaxies too massive too early, structures too smooth, constants too fine-tuned, and probabilities too rare to be explained by randomness alone. These weren't anomalies anymore. They were patterns. And patterns in the universe mean something deeper is at play. The closer we looked, the more we realized the universe wasn't just strange. It was too perfect. The laws of physics are so precisely balanced: gravity, electromagnetism, the nuclear forces, the cosmological constant, that if any one of them were even slightly different, galaxies wouldn't form, stars wouldn't burn, and life as we know it would be impossible. Why is the speed of light just right? Why does dark energy have the smallest non-zero value it could possibly have to still allow cosmic structure? Why is the universe comprehensible at all? These questions aren't just philosophical, they're cracks in the very logic of existence. And into those cracks poured new theories, some wildly imaginative, some terrifyingly rational, each offering a different way to explain the impossible precision of reality. One of them is the multiverse. What if our universe is not the only one? What if it is one bubble among countless others, each with different physical constants, different dimensions, different timelines? According to eternal inflation, proposed by Andre Lind, the inflating space that birthed our cosmos never truly stops. Instead, it continually spawns new pocket universes in a fractal foam of endless creation. In one, gravity is stronger and stars die too quickly. In another, there are no atoms. In yet another, life forms in ways we can't even imagine. Our universe, then, is not the center of anything but a statistical inevitability. Just one version where the conditions happen to support observers capable of asking why they exist. The multiverse doesn't just solve the fine-tuning problem, it reframes it entirely. It says, of course we live in a universe that permits life. Where else could we be? This is known as the anthropic principle, and while it seems like a tautology, it holds weight in a cosmos where infinite variation is possible. But the multiverse, for all its explanatory power, comes with a cost. It is, by nature, untestable. We may never see these other universes, never interact with them, never find evidence beyond indirect inference. And so the question lingers, is it science or is it cosmological mythology? Just when that debate threatened to tear physics apart, another, even stranger idea re-emerged from the shadows, not from the stars, but from the circuits of our own creation. The simulation hypothesis, popularized by philosopher Nick Bostrom and embraced by minds like Elon Musk and Neil deGrasse Tyson, suggests that our universe is not physical at all but computational. That what we perceive as atoms and energy are actually bits and logic gates in a vast simulation run by a higher intelligence or a future civilization. The reasoning is deceptively simple. If it becomes possible to simulate conscious beings in computers, and if advanced civilizations have the resources to do so, then statistically, it's far more likely we are inside such a simulation than the original real universe. The strange behavior of quantum mechanics superposition, observer effects, entanglement begins to look like code efficiency, like systems rendered on demand. The cosmic speed limit, the Planck scale, the apparent pixelation of space-time itself could all be features, not bugs, boundaries, not mysteries. And if we're in a simulation, then the universe isn't just a story, it's a script. But who or what is writing it? Are we NPCs, deterministic and blind, or are we real agents in a sandbox reality with the illusion of free will? These questions aren't just hypothetical anymore. Scientists are seriously exploring ways to test whether our universe has underlying digital structure, whether there's a mathematical fingerprint too perfect to be natural. And once you allow for that possibility, the existential terrain becomes volcanic. Because if the simulation hypothesis is true, then every law of nature is arbitrary. Every physical constant is code. And death, entropy, distance may all be constraints written into the architecture of the system. We may be more like software than stardust. But whether we live in a multiverse or a simulation, the result is the same. Our idea of reality is shattered. We are no longer physical beings in a physical universe. We are perspectives inside a vast informational structure. And just when this revelation seems too vast to carry, it tightens into something profoundly personal. Because what matters now is not just what the universe is, but why it contains you, you capable of thought, of wonder, of love, and terror, and dreams. You aware not just of light and sound, but of time, of meaning, of questions, so deep they rupture language itself. In every version of the unexpected twist, one thing becomes clear. Consciousness is not an accident. It is not a passive effect of neurons or molecules. It is the most unlikely thing the universe has ever produced. And yet, here it is burning behind your eyes. The simulation hypothesis reframes consciousness as a core feature in intended output. The multiverse suggests it is rare, valuable, improbable beyond belief. In either case, we matter. Not because we are central, but because we are awake. And if the universe is information, and we are part of it, then consciousness may be the universe folding back in on itself, looking inward for the first time. This is the deeper twist, not that we're small, but that we belong. Not that we're lost, but that we are embedded in something stranger and more beautiful than we ever imagined. The universe may not be real in the way we once thought, but the experience of it, the act of beauty, the pull of mystery, the quiet thunder of always, more than real. It is sacred, and perhaps the final twist is not found in theory or data but in emotion. In that moment of stillness when you look up at the stars and realize that the thing you are staring into is not indifferent, it is you. And whether we are pixels or particles, simulations or souls, the universe wants to be known. That is why it gave rise to minds, to story, to science, to search. And so we continue, not because we expect a final answer, but because the questions themselves are the fire. Because the twist isn't the end. It's the beginning, and somewhere beyond this page, this paragraph, this breathe very thing changes again. We stand now at the edge of everything we've known, staring into a future where the questions have grown bigger than our tools, where reality itself seems to bend away from our reach. And yet we are not done, we are only beginning. Because after all the revelations, the paradoxes, the simulated shadows and infinite multiverses, we are left with a challenge more formidable than any black hole or quantum singularity. How do we keep going when the universe keeps running ahead of us? The challenges facing the next era of cosmic exploration are not just technical, they are conceptual, philosophical, existential. We've outgrown the instruments we built to understand the old universe, and now we need tools to understand the new one. The telescopes that brought us the light of ancient galaxies now tremble at the edge of their sensitivity. The detectors that once cracked open gravitational waves now long for quieter environments, deeper vacuums, finer resolution. Our questions have become so precise, so cosmic in scale, that Earth itself is no longer a sufficient laboratory. The atmosphere, with all its beauty, blurs the sharpest light. Our magnetic field deflects high-energy particles. Our gravity tugs on the mirrors and optics with relentless indifference. Even in orbit, our current observatories can only see so far-infrared, ultraviolet, microwave, each with their limitations, each straining to gather photons that began their journey billions of years ago. And time is against us. The light we seek grows fainter every moment. Galaxies drift farther. Space expands faster. The early universe becomes more elusive with every passing year. We are chasing echoes across a sea that stretches wider by the second. The questions we face now demand instruments of extraordinary ambition, telescopes that can image exoplanet atmospheres in other star systems, that can detect biosignatures, industrial pollution, alien chlorophyll. We need missions that can map the structure of dark matter, not just statistically, but directly, gravitationally, holographically. We need gravitational wave observatories in space like the Laser Interferometer Space Antenna, LISA, spanning millions of kilometers, so sensitive they can detect the whispers of colliding black holes from the dawn of time. We need a cosmic neutrino observatory, something that can register particles so ghostly they pass through planets undisturbed, particles that may carry information from the very edges of our light cone. We need quantum sensors that use entanglement to detect curvature in spacetime with microscopic accuracy. And to do all this, we need to leave Earth behind, permanently. We need dark-side observatories on the Moon, shielded from Earth's noise. We need telescopes stationed at Lagrange points, stable gravitational pockets, far from interference. We need deep space probes powered by nuclear fusion or antimatter propulsion, capable of traveling for centuries, relaying data from beyond the Oort cloud, from interstellar space, from the void between galaxies. And all of this depends on something more fragile than rocket fuel: funding, focus, imagination. Because science doesn't just require knowledge, it requires belief. Not faith in answers, but in the value of questions. And right now, we face hurdles beyond physics: political apathy, economic distraction, the temptation to look inward as the cosmos calls us outward. Yet the challenges ahead are too important to ignore. For instance, we still don't know what dark matter is. We know it exists, its gravitational effects are everywhere, but we have no particle to match it. WIMPs, axions, stereo neutrinos none have shown up. The Large Hadron Collider, for all its brilliance, has yet to find physics beyond the Standard Model. Supersymmetry, once the favorite child of theory, now sits wounded, unconfirmed. Meanwhile, dark energy, the mysterious force accelerating the universe's expansion, remains even more elusive. Is it constant? Is it dynamic? Is it a new field? Is it a crack in Einstein's theory? We don't know. We need next-generation missions like Euclid, Nancy Grace Roman Space Telescope, and the Vera Rubin Observatory, designed to map dark matter and measure cosmic acceleration with unprecedented detail. But even with these, we may only scratch the surface. We also need better quantum gravity models. Loop quantum gravity, string theory, emergent spacetime, causal sets all are promising, but none are complete. And worst of all, none are testable. The Planck scale of the realm where gravity and quantum mechanics collidias kiminen menometas kiminers. We are many orders of magnitude away from ever probing that scale. How do we study a reality we can't reach? This is a profound hurdle, but not a hopeless one. Some propose indirect tessusing the early universe as a natural collider. The cosmic microwave background may carry imprints of Planck-scale physics, buried in polarization or non-Gaussianity patterns. Others suggest entangled black holes or wormhole analogues could reveal the fabric beneath space itself. We must be creative. We must be radical. Because the truth may not lie in bigger machinists, but in cleverer questions. The other great challenge is time. Not time as we experience it, but time as a physical quantity. We still don't know what time is. Is it an illusion, a dimension, an emergent artifact of entropy? In quantum cosmology, the wave function of the universe doesn't even require time. It exists outside it. That breaks everything we thought we knew. It requires a rethinking of causality, of sequence, of the arrow we follow through life, and perhaps most daunting of all, we still don't know what consciousness is. Not truly. And that matters because we are trying to use a mind to understand a universe that may be inseparable from the act of observation. If quantum mechanics is real, and observation affects outcome, then the mind is not irrelevant, it is part of the system. But how do we incorporate subjectivity into objectivity? How do we build science that includes awareness without collapsing into mysticism? That is a challenge no telescope can solve. Only time, dialogue, and courage can. The last challenge is philosophical, but it may be the most important. We are approaching questions that may not have final answers. Not because they're unimportant, but because they transcend the format of answers entirely. What lies beyond the universe? What happened before time? Is there a theory of everything, or only a theory of everything we can observe? Are we living in a simulation? If so, can we reach the source code? And if not, what does that mean for meaning? These aren't dead ends, they are thresholds. And the next era of science will not be defined by how much data we collected, but by how brave we are in crossing them. Scientists are preparing. They are building the frameworks for next-gen missions, collaborating across continents, designing quantum experiments that defy imagination. They are proposing Einstein telescope projects, neutrino observatories beneath the Antarctic ice, space-based quantum communication, dark matter detectors the size of cities. They are pushing for AI-driven simulations of cosmic inflation, of multiverse collisions, of galaxy-scale feedback systems. And they are not just physicists. They are engineers, coders, artists, philosophers, storytellers. Because the next chapter of discovery is not just technical, it's human. And it will require every ounce of creativity, cooperation, and compassion we can summon. The hurdles are enormous, but so is our will. We are the only species we know that looks at the void and says, "Let's go." We are the only creature that builds machines to listen to black holes, that deciphers the light of dead stars, that puts names to galaxies we will never reach, that sends golden records into interstellar space, hoping something might hear. And that's the most beautiful challenge of all. To keep asking, to keep building, to keep reaching not for conquest, but for connection. Because the universe doesn't owe us answers, but it has never stopped whispering. and now it's our move. This is the final confrontation not with a villain, but with the universe itself, or rather, with our fractured and incomplete understanding of it. Split between two towering pillars of modern physics that both explain the world perfectly within their domains, and yet, when brought together, collapse into contradiction like incompatible gods forced to share the same temple. On one side stands general relativity, the majestic theory of space-time and gravity, formulated by Einstein and tested for over a century with stunning precision from the bending of starlight around the sun, to GPS satellites accounting for time dilation, to gravitational waves rippling through the cosmos after black hole mergers billions of light years away. It is a theory of smooth curves, continuous geometry, and mass shaping the stage of reality. On the other side stands quantum mechanics, the rebel genius of the subatomic world, unpredictable, probabilistic, full of paradoxes, where particles are waves and waves are probabilities, and nothing is certain until it is observed. It gave us semiconductors, lasers, the standard model of particle physics, and it governs everything from atoms to quarks to the vacuum itself. These two theories are not rivals, they are enemies of unity. They refuse to share the same language. Where relativity is geometric and deterministic, quantum mechanics is algebraic and indeterminacy. And yet both must be true, because both keep predicting reality with supernatural accuracy. But the moment we try to apply both to the same phenomenon like a black hole or the origin of the universe, they scream in contradiction. General relativity predicts singularities, points of infinite density, where time and space stop making sense. Quantum mechanics forbids them. Relativity assumes a smooth continuum of space. Quantum theory insists space is granular at the smallest scale. And so the deepest minds of our time have been trying to bridge them, crafting theories of quantum gravity that might unite the cosmic and the microscopic into one elegant architecture of being. And in this Airneth final confrontation of modern physics, four great contenders have stepped forward. First is string theory, once the darling of theoretical physics, positing that particles are not point-like, but vibrating strings existing in a 10 or 11-dimensional space-time. It promised unity, gravity, electromagnetism, strong and weak nuclear forces all emerging from the same underlying symmetry. It offered black hole entropy calculations, dualities, and the holographic principle. But it also came with an enormous baggage of untested assumptions, a landscape of Kuminen, visisata possible universes, and no definitive predictions. Beautiful, yes, but elusive. Then there's loop quantum gravity, an attempt to quantize space-time itself, to describe it not as a smooth fabric, but as a network of discrete loops. Like atoms of space, it avoids singularities. It predicts a big bounce instead of a big bang. It's background independent and free of extra dimensions, but it struggles to unify all forces and hasn't yet shown how it connects with known physics at high energy scales. The third path is causal set theory, which suggests that space-time is not continuous at all, but a discrete set of events ordered by causality, a kind of cosmic blockchain. It's simple, elegant, and potentially compatible with relativity, but remains largely theoretical and mathematically difficult to evolve. And then, growing in popularity, are emergent space-time theories, built from ideas like entanglement entropy, tensor networks, and ADS, CFT duality. These suggest that space and time are not fundamental, but emerge from quantum information itself, from the entanglement patterns between microscopic bits. In this view, the geometry of the universe is a macroscopic expression of a much deeper quantum code. This is where relativity and quantum mechanics might finally converge in it by compromising, but by realizing that both emerge from a common source. Yet none of these theories have been proven. None have been tested, and all face the same brutal truth. We do not yet have the experimental tools to verify them. The Planck scale, where quantum gravity lives, is beyond our colliders, beyond our detectors, beyond even our deepest cosmological observations for now. But even without a final answer, the confrontation rages on in journals, labs, observatories, and minds across the globe. And at the center of it is a single question that divides cosmologists like a blade through space-time. Will we ever find the true boundary of the universe? Not just the observable horizon, but the actual edge if such a thing exists. Some argue yes. They point to the acceleration of the universe, the imprint of inflation, the boundary conditions of the CMB, and say, we can extrapolate, we can map the topology of the cosmos. We may even detect collisions with other universes through supple anomalies. Others say no. That space may be infinite, or closed without edge, or emergent altogether, meaning the question of a boundary is ill-posed, like asking what lies north of the North Pole. And still others say, the boundary is not spatial, it is informational. It lies at the limit of what can be known, not what can be traveled. The holographic principle supports this view that everything inside a region is encoded on its surface, and so the edge may be the true universe, with what we perceive as volume being an emergent illusion. In this confrontation, even our role as observers is in question. Because if reality is informational, if it is generated by entanglement and governed by computation, then the observer is not an afterthought. It is a key player. It means we are not outside the system looking in. We are part of the system rendering itself. This changes everything, because it means the future of cosmology isn't just about instruments. It's about interpretation. It's about asking better questions. We used to believe the sky was a dome. Then we believed it was infinite. Then we believed it had an edge. Now, we believe it may be a process of holographic computation we only experience from the inside. And this new perspective is already shaping the next generation of missions. The James Webb Space Telescope is revealing galaxies that form too fast, challenging our models of early star formation. The Nancy Grace Roman Space Telescope will explore dark energy with vast surveys. LISA will listen to black holes from the earliest epochs. Vera Rubin will track the sky for signs of dynamic dark matter. But the greatest breakthrough may not come from space, it may come from entanglement. Quantum simulations, quantum computing, and quantum networks are teaching us that the structure of reality may not be made of matter at all, but of relations. And in that framework, space-time is not a thing but a story, a pattern of connections, projected from deeper code. That is the final confrontation. Between old assumptions and new paradigms, between classical geometry and quantum logic, between the universe as container and the universe as computation. And through that battle, we begin to glimpse something greater, not an answer but a possibility. That maybe, just maybe, the real frontier is not the edge of the universe, but the edge of thought. That to unify physics, we must first unify perspective as. That the future of cosmology lies not in dominating space, but in understanding the language it speaks. And that language, it turns out, may not be math alone. It may be logic, yes, but also information, consciousness, complexity, beauty. Because if the universe is indeed a quantum computation, if reality is a self-generating pattern of encoded relationships, then everything we are, everything we do, and everything we dream matters. Not because we're at the center, but because we are the only part of the cosmos capable of seeing the whole. The final confrontation, then, is not a war, it is a revelation. That the quest for the edge was never about reaching a wall. It was about reaching a point of reflection. A place where the universe, for one fleeting moment, saw itself and wondered what it could become. In the end, after the equations are exhausted, after the simulations fade, after the light from distant galaxies finally grows too faint to follow, the universe leaves us not with a conclusion, but with a quiet invitation. Remember why you looked up in the first place. Because beyond all the science, beyond the telescopes and black holes and holograms and simulations, lies something older than knowledge, is something deeper than data, something so human it transcends the boundaries we spent lifetimes trying to measure. That thing is curiosity, a flicker in the dark, a question with no promised answer, a hunger that asks not just, what is this? But what does it mean that I'm here to ask at all? The moral of our cosmic journey is not that we will ever know everything. It's that we never had to. The value was never in reaching the edge of the universe. It was in daring to chase it, to feel that gravitational pull toward the unknown and follow it, even when it frightened us, even when it humbled us, even when it shattered our favorite theories and left us holding paradoxes instead of answers. That's where progress lies, not in certainty, but in the courage to live without it. The stars did not owe us secrets. The galaxies did not promise us meaning. But we looked anyway, because that's what it means to be human. To stand in a void so vast and uncaring, and still whisper into it, "I want to understand." We mapped the skies not to control them, but to feel connected to them. We studied atoms not to reduce life to particles, but to glimpse the architecture of wonder itself. We built observatories, ran collidors, tested every model we could imagine, and not because we expected the universe to explain itself, but because we wanted to participate in its unfolding. Every breakthrough, every theory, every Nobel Prize was born not from perfection, but from persistence. From minds who sat with discomfort, with failure, with impossibility, and asked anyway. From Galileo, who risked his freedom to prove the Earth moves. From Einstein, who rewrote space and time in his imagination. From women like Vera Rubin, who saw dark matter in the curves no one else dared to trust. From the teams of engineers, janitors, coders, thinkers who sent metal eyes into space and waited years for the light to return. We did not reach the cosmos because we had all the answers. We reached it because we refused to stop asking. And that refusal, that fire in our chest, that quiet, what if, is the moral spine of everything we've done. It teaches us that science isn't cold, it's sacred. It's not the opposite of emotion, it's one of its highest forms. It is love for truth. It is devotion to process. It is reverence for a reality that never had to include us, but somehow does. And even when it reminds us how small we are, it also reminds us how rare we are. Because we are the only known species to look at a black hole and wonder not just what it is, but what it means. We are the only known life form to build stories from math, to extract poetry from particles, to find awe in a beam of light that traveled comatose a billion years just to touch our retina for 1 second. That awe matters. It matters in a world growing numb, where attention spans flicker and division rises, where the immediacy of life tempts us to forget the vastness of it. The cosmos restores that perspective. It reminds us that we are not the center. But we are not meaningless either. We are context. We are the consciousness of the universe localized in time, wrapped in carbon, moving through entropy with questions no machine can replace. And perhaps that's the final balance, is that truth walks hand in hand with mystery. That the more we know, the more we realize how much there is left to feel. Science gives us the tools to measure the sky, but it's wonder that makes us look up. Knowledge gives us theories, but mystery gives us purpose. And together, they form a loop knot unlike the universe itself, where every discovery opens a new unknown, and every unknown calls forth a new kind of discovery. That loop is not a trap. It is a gift, because it means we will never run out of reasons to keep going. The edge of the universe may remain forever out of reach. We may never know whether we're a hologram, a simulation, or a bubble in a multiverse sea. But in asking those questions, in building the language to even ask them, we become more than flesh. We become storytellers of the infinite. And that is a kind of immortality no theory can erase. So if there is a takeaway, the moral arc of cosmology bends toward any one truth. It is this: wonder is worth it. Curiosity is sacred. And mystery is not our enemy. It is our origin. It is our home. And in exploring it, we don't diminish ourselves. We define ourselves. Not by how much we conquer, but by how deeply we care to understand. That is what the stars have been trying to teach us all along. So, after everything, the collisions and paradoxes, the black holes and boundaries, the equations, and the awe, we dare close the book, or do we leave the last page blank, knowing that the true ending was never the goal, but the momentum to keep turning pages long after the light fades? Because that's the question now. Should the mystery remain open-ended? Or are we so addicted to resolution that we can't bear to leave the cosmos unfinished? But here's the deeper truth: the universe is unfinished, and perhaps always will be. That is not a flaw in the story. That is the story. It's a universe that doesn't close, it expands. Not just in volume, but in meaning. Not just in space, but in perspective. Every time we think we're nearing the edge of knowledge, we find another horizon, another twist, another what if, glowing in the dark like a newborn star. And maybe that's the point. The value of a question isn't always in the answer, it's in how it reshapes us while we seek it. We began this journey staring into the night sky, wondering what lies beyond, searching for edges and boundaries, for singularities and beginnings. But what we found instead was a mirror that reflected not just galaxies, but ourselves. Our need to know, our fear of not knowing, our willingness to stand in front of the infinite and still ask. And that's why the mystery must remain open, because it is the breath of discovery, the rhythm of science, the heartbeat of imagination. When we leave questions unanswered, we do not fail, we invite. We leave space for new minds, new questions, new generations to pick up where we left off. And that, more than any answer, is the legacy of exploration. Because in the end, what matters most are not the conclusions, but the courage to live inside the questions. That is what built every telescope. That is what drove every theory. That is what turned ancient stargazers into physicists, philosophers, and dreamers. We did not climb the mountain of knowledge to plant a flag, we climbed to see what was beyond it. And we found more mountains. The biggest takeaways from this journey were never just facts. Yes, we learned that the universe is accelerating, that dark energy shapes our fate, that black holes radiate, that space might be holographic, that time might be emergent, that multiverses might bloom like flowers beyond our cosmic garden. But more than all of that, we learned that reality is deeper than understanding, that the structure of the cosmos is not just out there, it's entangled with our need to ask, to observe, to make meaning. That we are not just in the universe, we are participants in it. This is what science has taught us, that curiosity is not a weakness, it's the engine of civilization. That doubt is not an obstacle, it's the ladder we climb. That humility in the face of the unknown is not surrender, it is the highest form of respect. So when people ask, will we ever find the final theory? The edge of the universe? The source of it all? Maybe the wisest answer isn't yes or no. But why do we want to? What are we trying to find? Closure? Control? Or something more profound? Connection? Because when you look at the stars now, knowing all this, the simulations, the multiverses, the expanding foam of inflation, the ghost particles and gravitational whispers, do you feel smaller? Or do you feel larger, knowing you are part of something that cannot be boxed, explained, or concluded? Because that's the quiet miracle at the heart of cosmology. It began as a study of the sky. It became a story of us. The atoms in your hand were forged in dying stars. The thoughts in your mind obey quantum laws. The light you see began before Earth even existed. You are the cosmos, briefly aware of itself, and that awareness matters. It is the rarest thing we know of. And if the universe goes on forever, if it never ends, if it never tells us what it's all for, that doesn't make it less beautiful. It makes it more alive. Because a story with no ending is a story that belongs to everyone. And the universe is not a riddle waiting to be solved. It is a mystery waiting to be lived. So maybe we don't need a final answer. Maybe we don't need to seal this narrative with a truth carved in stone. Maybe the best thing we can do, the most honest, the most human, is to stand at the edge of knowledge, look out across the unknown, and say, to be continued. Because the cosmos is not finished, and neither are we.